Here we're going to talk about an economic concept called elasticity of demand. As most familiar with, if you have a product that you're selling, the more of those things that are available on the market, the lower the price. This graph represents that. And this is sort of a general trend in capitalism. It's how it kind of works most of the time. There are exceptions, of course. We call this the demand curve, which is technically the price getting lower as the more and more number of units or surplus increases. To talk about the elasticity, what that means is how responsive is the price to changes in surplus. For example, suppose we had a 4% increase in surplus, we would expect that to cause a drop in price. Now, would that be a 4% drop in price? It might be. If that were the case, we would say the elasticity of demand is 1. Technically, the elasticity is the percentage change in, sorry for the pause here, it's the percentage change in surplus divided by the percentage change in price. So 4% divided by 4% is the number 1. And we call this unit elasticity, meaning a value of 1. But there are certain products for which other things can happen, like there are certain products where if you had a 10% increase in surplus, that would only cause a 2% drop in price. And in this case, the drop in price is not particularly responsive to the increase in surplus. And so we say that there's an elasticity less than 1, in this case 1/5, which came from 2 divided by 10, essentially. But there are other products that go the other way and have an elasticity higher than that. So for example, suppose there was some product that price was so sensitive to increases in surplus where only a 2% increase in surplus caused a 6% drop in price. In this case, we would say it is more elastic, or that it has an elasticity higher than 1. You'll notice here 6 divided by 2 is 3. This is sort of the notion of what elasticity means. Now, in the calculus class, you don't technically need to know any of this. You just need to know how to do the problems. But I thought if we were going to talk about elasticity of demand, you should at least know what it is we're measuring. So if you got a little bit lost there, don't worry. Look at the graph here, and suppose we were to use the variable x for the number of units that are available for sale or surplus, sort of the supply on hand. And let's let P represent the price of this particular item. Now, using those variables, suppose we had this as our elasticity of demand. Now, in the examples above, the elasticity was a number. And there are products where that's constantly the case, where for a particular thing you're selling, the elasticity is just 3. All the time. Every time you have an 1% increase in surplus, you have a 3% drop in price. But those situations are more rare. It's more likely that the elasticity of demand will depend on how many items you have in surplus. So you can see that in general, we might think that how elastic the demand is, in other words, the responsiveness to price as a function of the number of units increasing would depend on the number of units that were already available. And so it's pretty typical for you to have elasticity as a function of x, which is the number of items in surplus. For example, if we were to use this formula for a particular product, well, suppose we were to plug 200 into this formula. I did the arithmetic, I got 3/5. What that means is that if there are 200 units available, that the product, the elasticity of demand is lower than 1, which means that the price is not particularly susceptible to the number of changes in the number of units. But for the same product, it may be the case that for other supplies, suppose there were 180 units available, that there might be an elasticity of exactly 1. And by the way, I plugged 180 into this formula, and I happen to get 1. But there are other points in the demand curve. For example, if there were only 90 units available, and notice that now that we're getting lower in the number of units for sale, that the elasticity might be much higher than 1. In this case, I plugged 90 into the formula and got 5, which means when we're at a relatively low supply like that, 90, that all of a sudden the price becomes much more responsive to changes in the surplus than it would have otherwise. So if you got a little lost here, this is sort of economics 101, and don't feel bad if you don't understand every detail, but the takeaway here is that elasticity, meaning the how responsive the price is to changes in surplus, can vary depending on the surplus itself and is often therefore a function of X or surplus. Now, that's sort of the economics of elasticity. That's sort of what you saw there was the economics of elasticity. But what you particularly need to know for this course, that calculus course that you're taking right now, is how to solve the problems. And that's what we're going to get into right now. I'm going to give you an actual example and show you the differential equation that you would solve to do this. The first thing you need to know and memorize, frankly, for this course is the formula for elasticity in terms of differentials. Now, this may look strange to a calculus student, and what does all this mean? So I want to break down this formula as to what it means. When I'm done breaking it down and giving a description of the meaning, at the end of this, you technically don't need to know all that. You just need to know this is the formula and this is what you're going to use. But no sense giving a formula without telling a little bit about why it's there. So let's talk about each component part of it. The numerator here is the change in demand, dx or delta x, you could call it. The change in surplus, I meant to say. The percentage increase because we're dividing by the surplus itself. So that's what that differential fraction represents. It's the percentage of increase or decrease in the surplus or the supply. And if we divide that by the percentage increase or decrease in price, then that gives us our elasticity. We saw that in the previous example where we had a 2% increase in surplus and a 6% decrease in price, and we divided 6 divided by 2 to get an elasticity of 3. Another curious thing is, why is there a negative sign in the formula? Well, they could have defined elasticity without that negative sign, but the reason they chose to have a negative sign there is they wanted elasticity to be a positive number. It would have been confusing to run around and talk about an elasticity of -3 or -2/5. And just to make life easier and keep things positive, they put that negative sign in there. But here's an interesting question. Why would putting a negative sign in a formula make something positive? Well, because it turns out in almost all cases in capitalism, either the numerator or the denominator of this fraction is negative while the other one is positive. For example, if you have an increase in surplus, you're going to have a decrease in price. That would correspond to the numerator in red being positive and the denominator, the differential there, being a negative number. Or reversely, a decrease in surplus, meaning a negative numerator, would lead to an increase in price, meaning a positive denominator here. And so the idea is that the numerator and denominator differentials are almost always opposite signs. If one of them is increasing, the other one is decreasing. In other words, if one of them is positive, the other one is negative. So that fraction is almost always a positive divided by a negative, or a negative divided by a positive. Either way, that fraction is negative. And by putting a -1 multiplier in front of it, that simply turns it back into a positive in most cases. And that's the reason why that negative is there. Now, what you just heard is a description of why they created the formula this way. If you're not the kind of student who particularly likes those explanations or feels like you need them, technically you don't need to know any of that. It's nice if you do, but all you really need to know for this class is how to use the formula. You don't need, no one will ever test you on where that formula came from, as far as I know. I certainly wouldn't. So now let's get to the nuts and bolts of actually how to do this problem. So given the formula at the top, that was given in the problem, what we're going to do is set that equal to the elasticity formula. And this is the differential equation that we're now about to solve. So in order to solve this, there's a lot of mechanics here. I'm not going to explain each one in great detail, but you might want to, in real time here, hit pause at the end of each step so that your brain can catch up. Everybody thinks differently. Some of you are fast thinkers and some of you not. Okay, so here go all the actual mechanical steps. The first thing that is very helpful to do in a differential equation is to separate your variables, to get your p's and your x's on different sides. So I did some cross multiplication and some clever algebra here. Hit pause so you can analyze that. Okay, and now I noticed that the x's would cancel, and I did some rearranging there. Hit pause to analyze that. I'm going to stop saying hit pause, but you should continue to pause at each step and make sure that you're following. Now what you'll notice here is I've separated my variables. I have my p's on one side and my x's on the other. So I should take that equation and integrate both sides. This is how we do a separable differential equation, as you know from past lessons. So integrating both sides leads to this. I'm going to get a natural log in each case. Before you hit pause and try to analyze this, I may want to mention that on the right side of the equation, two things worth mentioning here. On the right side of the equation, I didn't show my work here, but I did a u substitution, and I let u equal 240 minus x. And also, when I did both integrals, I got a plus constant on both sides, but rather than writing it on both sides, we could just put all those constants on one side. So that's why I have it appears like I got a plus c on one side and not the other, but really we get a constant on both, but I can lump them onto one side. Now from this point on comes some tricky algebra, but you'll recall that I can solve an equation. Let me rephrase that. I can take an equation with natural logarithms and get rid of the natural logarithms by taking e raised to both sides of the equation. Here's a trick from pre-calculus. So actually, another trick first you'll remember is that if I have a multiplier in front of a log, I can bring that up above the argument as an exponent. And now I can raise e to both sides of this equation. And it may seem like, well, why would you want to make it even messier? Why raise e's to both sides? Well, as you're about to see, there's some great simplification that happens to the natural log here when I do this. And that is, well, first of all, I can, as we've seen before, I can get a constant multiplier of k here when I do that. You've seen this in previous videos of mine. And then I can simplify those e to the natural logs by canceling them out. Essentially, that e is the reverse of the natural log, and so we get a lot of cancellation here. If this is algebra that you're not super familiar with from pre-calculus and above, then not much I can say here at this point about it, but it is stuff from your past. But the important thing to notice here is that I've solved for the price as a function of the amount of surplus. But I have a constant k here, which originally came from my plus c. And in order to fully find the price as a function of surplus, I have to know what k is. Luckily, if you look at the problem, they tell us that when there are 115 items in surplus, the price is $50. So I can plug that information in, do a little bit of work. By the way, this would be a good time to remind you that raising something to the 1/3 power is a cube root, in case you forgot that. So I did some math and I found out that k is 10. And once I know the value of k, I can answer my question. The question says, what will the price be when there are 176 items in surplus? So to solve for that, I plug in 176. And again, remembering that the 1/3 power is the cube root and doing some basic PEMDAS here, I get that the price is 40. And that tells me that if there are 176 items available, that the price will drop from $50 in the original case to $40. And that completes this problem.